Welcome. We are going to discuss paracyclic reactions. We're going to review two types of paracyclic reactions, cycloadditions and electrocyclic ring opening reactions. Let's start with cycloadditions. There are numerous examples of cycloadditions. So we've looked at some already. We'll look at a few today, but there are lots and lots of examples. The good news is you treat the examples exactly the same. So even though there's lots of different examples, the way we go about figuring out whether they're allowed or forbidden is going to turn out to be pretty much exactly the same. It's important to note that cycloaddition reactions can be run under thermal and also photochemical conditions. And those are really just details, because in the end, whether it's under thermal or photochemical conditions, we're always going to do the same thing. We're going to focus on the frontier molecular orbitals of our two reactants. It's a cycloaddition, so there will be two reactants. This is a bimolecular cycloaddition reaction. So there'll be two species coming together to form a new ring. We're going to focus on the highest occupied molecular orbital of one of them and the lowest unoccupied molecular orbital of the other. And that's the way it always has to be, because the highest occupied molecular orbital is filled, the lowest unoccupied is empty. We need a filled orbital interacting with an empty orbital. It doesn't really matter if we choose the highest occupied molecular orbital of one reactant or the other, but whichever one we pick, we want to compare it to the lowest unoccupied molecular orbital of the other, the second. The only way you could make a mistake here, I guess, is if you chose the highest occupied molecular orbital and the lowest unoccupied molecular orbital of the same species. We don't want to do that. So we've got two species in a bimolecular reaction. Choose the HOMO of one and the LUMO of the other. Well, once we've done that, we actually have some choices about how we analyze. So using the classic Woodward-Hoffman treatment, we would simply look at those two orbitals, the highest occupied molecular orbital of one and the lowest unoccupied molecular orbital of the other, and we would ask the question, are they of the same symmetry? We define them as either symmetric or antisymmetric. If they're both symmetric or they're both antisymmetric, then they're of the same symmetry. If the answer is yes, they are both of the same symmetry, then the reaction is allowed, which means it should happen quickly, easily. If the answer is no, they're of opposite symmetries, then the reaction is forbidden. And what that means is that the reaction is not going to take place easily, that's for sure. At least the concerted cycloaddition is not going to take place very easily. If it happens at all, it will happen in a high energy process, probably in a stepwise process, not in a concerted process. It'll be much slower, and in some cases it won't happen. So you have to take these words allowed and forbidden with a little bit of a grain of salt, but they really tell us whether the reaction is facile or not, whether it's going to occur in a concerted fashion, it would if it's allowed, or whether it's going to be a high energy process if it occurs at all, which would be the case if it's forbidden. Generally speaking, the reactions that are allowed are the ones we're interested in. Frontier molecular orbital treatment is very closely related, but it's a little bit different than the Woodward-Hoffman treatment. Once again, we're going to focus on the frontier molecular orbitals, but rather than worry about their symmetries, we're just simply going to stack one of them on top of the other. So we would stack the highest occupied molecular orbital of one species atop the lowest unoccupied molecular orbital of the other, kind of like two pieces of sandwich bread, stacked one on top of another. Once we do that, we look carefully at the terminal carbon atoms of each of those pi molecular orbitals, and we see whether or not there are bonding interactions between the appropriate lobes that are approaching one another. If there are bonding interactions and only bonding interactions, then we'd say the reaction is allowed, to steal Woodward-Hoffman terminology. And if it's not the case, if there are anti-bonding interactions, one or more, then we would say it is forbidden. So we'll look at some examples of all of these. Let's start with this reaction. Here I have two different ethylenes. The first one is a tetrachloroethylene, and the second is a tetrabromoethylene, and I'm going to run this under thermal conditions, and you can tell it's thermal because I've got my triangle there, which implies heat. And there's no evidence of a photochemical reaction. You'd have to see H nu if it were going to be a photochemical reaction. And the question is basically, what would the structure of this cycloaddition product look like if it formed in the first place? And then secondly, will it form? Will this be an allowed reaction or will this be a forbidden reaction under these thermal conditions? Well, in this cycloaddition, I would be forming a four-membered ring, and my aeroformalism would look something like that. The product, if it forms, would be a cyclobutane, which would look something like that. So that's what the product would look like, but the question is this reaction allowed or forbidden? Well, in these cases, I have ethylenes. I know there's lots of halogens around, but we're only concerned with the pi molecular orbitals, so we're just going to focus on those. The chlorines and the bromines don't add any complexity at all to this problem. We're going to treat this from a pi molecular orbital perspective as ethylene reacting with ethylene. So if I stack the pi molecular orbitals for ethylene along this energy axis, I would go from pi 1 to pi 2. Pi 1 has no new nodes, and so we could shade up and shade up. Pi 2 would have one node. As we pass through the node, we have to change our shading. And for each of these species, there's two pi electrons involved. In other words, pi 1 would be occupied, but pi 2 would be unoccupied. Pi 1 is therefore the highest occupied molecular orbital, and pi 2 is the lowest unoccupied molecular orbital. So this is going to be the same for both species, because they're both ethylenes. So what do? Well, as we said, we simply compare the highest occupied molecular orbital of one species with the lowest unoccupied molecular orbital of the other. And we can do this in two ways. We could do the Woodward-Hoffman treatment, and so to do that, we would look at the highest occupied molecular orbital of one species, which is this one right here, and say, okay, is this one symmetric or anti-symmetric with respect to planes of symmetry that exist in the molecule? And I think whether you look at either the first or the second, you can very easily see that there is a plane of symmetry in the middle of the molecule, and this particular pi molecular orbital, pi 1, is symmetric with respect to that plane of symmetry. It has the same plane of symmetry. Pi 2, on the other hand, is anti-symmetric. That node is drawn right where the plane of symmetry would be, and you can see that one side is exactly the opposite of the other side, so this one is anti-symmetric. Now, coincidentally, since they both have the same picture, I don't have to draw this twice. All I really need to do is to compare the symmetries of the HOMO and the LUMO, and they're of opposite symmetries. So the prediction is that under thermal conditions, this reaction would not be allowed, it would be forbidden. That's the Woodward-Hoffman treatment. Now, the frontier molecular orbitals treatment is almost the same, except that it says, well, consider that when these things come together, they're going to stack like sandwich bread, and the p orbitals are going to overlap. And so it turns out on this drawing here, I've stacked my two pi molecular orbitals, pi 1 and pi 2. One is a HOMO, one is a LUMO. This could be the HOMO of tetrachloroethylene. This could be the LUMO of tetrabromoethylene. I've got them stacked on top of one another, and what I want to do is I want to see how these p orbitals interact, and I can see that there is a bonding interaction here. See, shading, shading. But over here, anti-bonding. And what that tells me is that this reaction would be forbidden. In order for this reaction to be allowed, using this kind of a treatment, I need to have bonding interactions on both sides. So that's an example of how we would use the frontier molecular orbital treatment as well as the Woodward-Hoffman treatment. We arrive at the same conclusion. You will always arrive at the same conclusion if you do it correctly. These are just different treatments, but they give the same answer every time. Well, that was the reaction run under thermal conditions. Let's look at the same reaction now run under photochemical conditions. we still have pi 1 and pi 2 for both reactants. Once again, since they're both ethylenes, this covers both of them. And pi 1 would look like this still. And pi 2 would have one node, one new node, and it would look like that. But we've got to consider carefully for either of these species what happens when we shine light. And so I'm going to redraw this here, where instead of drawing out the pi molecular orbitals, I'm just going to put a little line there representing the energy level of both pi 1 and pi 2. And I'm going to ask the question, well, where are the electrons? Again, it doesn't matter whether we're describing tetrachloroethylene or tetrabromoethylene because they're both ethylenes. This describes them both. For either one, the electrons, the 2 pi electrons, would reside in pi 1. And when you shine light, what you do is you promote an electron up to pi 2. So instead of having 2 electrons in pi 1, now I have 1 in pi 1 and 1 in pi 2. This initial electronic configuration would be known as the ground state, and after I shine light and promote an electron from pi 1 to pi 2, I have the excited state. Now, the ground state and the excited state are obviously different from one another. They look different. 2 electrons in pi 1 in the ground state, only 1 in pi 1 and 1 in pi 2 in the excited state. And moreover, they have different HOMO-LUMO values. For example, clearly, for the ground state, the HOMO is pi 1 and the LUMO is pi 2. For the excited state, the HOMO switches to pi 2 and the LUMO is undefined because there's not a pi 3. Now what I have to do in a case like this is I have to compare one HOMO and one LUMO, and I have to do it in the following way. It is highly unlikely, in fact pretty much impossible, that 2 excited state species would interact with one another. This is an important point. When you shine light on this solution that contains these molecules, the light could photoexcite either the tetrachloroethylene or the tetrabromoethylene, and it will, at different times, excite them both. There will be some excited state tetrachloroethylene floating around and some excited state tetrabromoethylene, but the lifetimes of the excited states is very short. And so once they're excited, they don't stay as excited state species for very long. They quickly fall back down into the ground state. They relax back down into the ground state. What this means is that the concentration of excited state species at any one given moment in time is always very low. And so the likelihood, the statistical likelihood that 2 excited state species are actually going to bump into each other and react with each other is really low. For all intents and purposes, we say that that just doesn't happen. Instead, what is much more likely is that 1 excited state species will interact with 1 ground state species. So that's an important feature of a cycloaddition reaction, which is bimolecular, involves 2 species, run under photochemical conditions. You're always going to compare 1 ground state species with 1 excited state species. And you have to also make sure that one of them is a HOMO and one of them is a LUMO. So in this case, since our excited state has a HOMO but no defined LUMO, because we're out of pi molecular orbitals, we're going to choose the excited state HOMO and interact that with the ground state LUMO. Okay, the excited state HOMO is pi 2. Is it symmetric or antisymmetric? It's antisymmetric. We're going to allow that to react with the LUMO of the other species, which is also pi 2, and it's also antisymmetric. So by Woodward-Hoffman rules, this reaction would be allowed. Let's look at frontier molecular orbital treatment. In this case, we would look at the highest occupied molecular orbital of the excited state species, which is pi 2. And we would allow it to stack on top of the LUMO of the other species, which in this case happens to also be described by pi 2. Now when we allow them to stack on top of each other, give yourself a fighting chance to be successful. In other words, it doesn't matter if you start on the left or on the right, but give yourself a bonding interaction initially. If this is pi 2 of the excited state species, which is the highest occupied molecular orbital for the excited species, then this one down here must be pi 2 of the ground state species. That's this pi 2, which is the LUMO. Give yourself a fighting chance. Set up a bonding interaction. If this one is unshaded, then this one would be shaded. And now as I pass through the node, this one has to be shaded up top. And lo and behold, when I do that, and I allow these things to stack like pieces of sandwich bread, I can see that the terminal lobes are interacting with only bonding interactions. So this is a winner. So whether we do it by the Woodward-Hoffmann rules or the frontier molecular orbital method, either way, we conclude that this reaction would be allowed. So it's very interesting. We looked at this very same reaction under both thermal and photochemical conditions. Under thermal conditions, it was forbidden. Under photochemical conditions, it is allowed. Let's look at another one. Here's a Diels-Alder cycloaddition. And I know we've looked at Diels-Alder cycloadditions before, but now that we've got this new information, it's useful to look at one more example. And in fact, the Diels-Alder cycloaddition is such an important reaction, you can never go wrong by spending a little bit of extra time looking at it. We're going to run it under thermal conditions, which is how it is run. And of course, it's run that way because it works well that way. But let's verify that it should work well. Now, another thing I want to point out here is that on our dienophile, I have this aldehyde present. It's actually very common on the dienophile to have an extra substituent which might have some pi electrons associated with it. But it doesn't change the fact that we're just going to focus on the electrons that are involved in the cycloaddition. There'll be 4 electrons on the diene and 2 electrons on the dienophile that are involved in a Diels-Alder cycloaddition. My aeroformalism would look something like this, such that the new molecule looks like this. And it doesn't really matter if this aldehyde group here, which is on this carbon, the same as that one right there, it doesn't matter if that's shown up or down. In fact, you would expect both outcomes. In other words, recognizing that this is a stereogenic center, we would assume that you would make a racemic mixture. How can you get both up or down? Well, that is a result of the fact that when you take the 2 pieces of sandwich bread, it doesn't really matter which one's on the bottom and which one's on the top. You can stack them like this or the other way around. And when you do that, you get the 2 different enantiomers. Okay, well, what we said is that we were going to look at the highest occupied molecular orbital of one and compare it to the lowest unoccupied molecular orbital of the other. Let's go ahead and choose the highest occupied molecular orbital of this butadiene. If you'd done it the other way around, it wouldn't matter. You'd get the correct answer. I'm not going to draw all the pi molecular orbitals. I'm just going to jump to the highest occupied molecular orbital. And what I know is that since there are 4 carbons, all of which are sp2 hybridized, and all of which have a 2p orbital contributing to this pi system, it's fully conjugated. There's a total of 1, 2, 3, 4 2p orbitals involved. 4 p orbitals in means 4 pi molecular orbitals out. There's pi 1, pi 2, pi 3, and pi 4. There's a total of 4 pi electrons. The first 2 would go into pi 1, and the last 2 would go into pi 2. In other words, pi 2 is the highest occupied molecular orbital under these thermal conditions. Pi 2 has 1 node, and there it is. And now I want to ask the question, is this thing symmetric or anti-symmetric with respect to planes of symmetry that already exists in this molecule? That node lines up with the plane of symmetry, and I think you can see that this is anti-symmetric. Now that I've looked at the highest occupied molecular orbital for my butadiene, I need to look at the lowest unoccupied molecular orbital for the other species, which is this ethylene. I know there's this other pi bond in here, but again, we're only focusing on the electrons involved in the reaction. We treat this like an ethylene. So I need to look at the LUMO for ethylene, which would be pi 2. So ethylene looks like this. I need to focus on pi 2, which would be the LUMO. Pi 2 would have a node. And once again, if we compare that to the symmetry which would exist in regular old ethylene, forgetting about the aldehyde, just thinking about the simple case of ethylene, there is a plane of symmetry in the middle of the molecule. And this node represents where that plane of symmetry would be. We can see that this is clearly an anti-symmetric pi molecular orbital. So this LUMO and this HOMO are both anti-symmetric. By Woodward-Hoffman treatment, this reaction would be allowed. Now let's think about it in terms of frontier molecular orbital treatments. What we would do is we would draw the HOMO of one and stack it on top of the LUMO of the other. So I've already got my pi 2 drawn here. Now I'm going to redraw pi 2 for my LUMO over here. But once again, I want to do it in such a way that I give myself a fighting chance. Since this is unshaded, I'm going to leave that unshaded so that I set up a bonding interaction, which means that that one must be shaded as I pass through a node. This one must be shaded, and lo and behold, there's another bonding interaction there. So my frontier molecular orbital treatment also predicts that this is allowed. Now, something to note here is that I'm only looking at the terminal carbons of both pi molecular orbitals. There are other carbons that have p orbitals here in the interior of the molecule, but this is the site of new bond formation. The new sigma bonds are going to form there and there. So those are the ones I focus on. And this one, which is facing down, is got a bonding interaction with this one, which is right below it, and same there. So this is all bonding. If we go back to our original aeroformalism, we're talking about these bonds right here. These are the new bonds in my molecule. I can boldface them. Those are the new bonds that are forming, and those are the ones that I focus on down here. So whether you use the Woodward-Hoffman rules or the frontier molecular orbital treatment, you arrive at the same conclusion, which will always be true. And in this case, the conclusion is that the reaction is allowed. Okay, one more example of a bimolecular cycloaddition. This is an odd one. We've got two butadienes, and we're going to allow them to react under photochemical conditions. So, clearly I would be forming new bonds there. I'll use my aeroformalism to see where all the pi electrons go. The product would look like this. This aeroformalism tells me there'd be a pi bond there, and this one tells me there'd be a pi bond there, and of course these are the new carbon-carbon sigma bonds. So there you have it. This would be a 1,5 cyclooctadiene. All right, now what we've said is that we have to identify the HOMO and the LUMO orbitals, the HOMO of one, the LUMO of the other, and compare them. So let's look at the HOMO of butadiene. We know that that must be pi 2. Pi 2 will be the highest occupied molecular orbital for this species. So let me go ahead and draw pi 2 right here. Pi 2 would have one new node. It would look like that. Is that symmetric or anti-symmetric with respect to planes of symmetry that exist in this molecule? Anti-symmetric. Okay. But I'm running this under photochemical conditions, so what I've really drawn here is pi 2, which is the HOMO for the ground state species. I need to consider what would be the LUMO for the excited state species. Remember, under photochemical conditions, we're going to choose one ground state and one excited state. One of them has to be the HOMO, one of them has to be the LUMO. It doesn't matter which way you go. In this particular instance, we're going to have some options. We didn't have options when we looked at ethylene because we were running out of pi molecular orbitals. So if you go back and look at that part of the video, we had to choose the HOMO for the excited state species. There was no LUMO. But here there will be both HOMO and LUMO orbitals available for the excited state species. So for example, what am I talking about? Let's look at an energy axis again. We'll first start with the ground state. Pi 1, pi 2, pi 3, pi 4, 1, 2, 3, 4. Then we shine light on it. When we do that, we promote an electron from pi 1, from pi 2 to pi 3, such that the excited state would look like this. There'd still be 2 electrons down there in pi 1, but when I shine light, I promote an electron from pi 2 to pi 3. Now there's only 1 electron in pi 2, and there's 1 electron in pi 3. For the excited state, the highest occupied molecular orbital is pi 3, and pi 4 becomes the lowest unoccupied molecular orbital. Over here, back in the ground state, the highest occupied molecular orbital was pi 2, and the lowest unoccupied molecular orbital was pi 3. All right, what have I done so far? So far I've looked at pi 2, which is the highest occupied molecular orbital of the ground state. I've now got to compare that with the lowest unoccupied molecular orbital. There must be one highest occupied compared with one lowest unoccupied of the other species, which would have to be the excited state species because I've already chosen the ground state. And we can see over here that the lowest unoccupied molecular orbital of the excited state would be pi 4. So pi 4 of the excited state species is what I'm after. Well, pi 4 has 3 nodes. Up, down, up, down. That's pi 4 of the excited state species. Is it symmetric or anti-symmetric with respect to this plane of symmetry which exists in the molecule? That node right there is at the same spot as the plane of symmetry we're considering, and you can see that everything on the left is exactly the opposite of everything on the right. It is anti-symmetric. That is exactly what we had for the highest occupied molecular orbital of the ground state species. They're both anti-symmetric, and therefore we would predict that they will in fact react in an allowed fashion with one another. So this reaction, this cycloaddition, is allowed. You can make a cyclooctadiene in this fashion, photochemical reaction involving 2 butadienes. Now, what if we did the other method, which is the frontier molecular orbital treatment? What we have to do here is we have to turn the molecule around so that we allow the terminal atoms to interact with one another. And we've looked at, this one is the pi 4 of the excited state species. Now we would need to compare that to pi 2 of the ground state species. So we're going to compare that to pi 2. Pi 2 would have a node right there. Give yourself a fighting chance, as always. Set up a favorable interaction. If this is unshaded, this is shaded and shaded. Now we pass through a node. Shade moves up. Lo and behold, 2 favorable interactions. Frontier molecular orbital method suggests exactly the same thing as the Woodward-Hoffman treatment, namely that the reaction is allowed. Okay, let's move on. Let's talk about electrocyclic ring opening and ring closing reactions. As was the case with the cycloaddition reactions, there are going to be numerous examples here. These reactions, once again, can be run under either thermal or photochemical reaction conditions. The way we treat them is a little bit different, though. You see, unlike a Diels-Alder reaction or another cycloaddition reaction, which is bimolecular, these electrocyclic ring opening and ring closing reactions are unimolecular. They involve only one species. So you can't compare the HOMO of one with the LUMO of the other because there's only one species in the reaction. So we do it a little bit differently. What we do is we always examine the highest occupied molecular orbital of the ring-opened molecule. That's going to be our best method. And we simply ask the question, looking at that highest occupied molecular orbital of the ring-open molecule, is the ring closing reaction going to be conrotary or disrotary? Whatever the answer is, it applies to the reaction in both directions. So in other words, if you're looking at this as a ring closed species, which is ring opening, it's still going to be conrotary or disrotary, whatever we determined by looking at the ring open species. That's going to tell us something about the stereochemistry of substituents, which is an important part. So let's just look at an example. Here I have a hexatriene, which I'm now treating under photochemical reaction conditions. And the question is, what would the product look like? And is the ring closing reaction, conversely, in the opposite direction, the ring opening reaction, is it conrotary or disrotary? Well, this is going to form a new six-membered ring. And you can see that I've kicked pi electrons there and there. So that would be the product. That's what the product would look like. And the question is, does it occur in a conrotary or a disrotary fashion? I want to look at the highest occupied molecular orbital, which under these photochemical conditions would not be pi 3. If we were under thermal conditions, since there are 1, 2, 3, 4, 5, 6 carbon atoms in this molecule, all of which have a 2p orbital associated with them, I need 6 pi molecular orbitals to describe this system. There's a total of 6 pi electrons also involved, so the first 2 would be in pi 1, the second 2 would be in pi 2, and the last 2 would be in pi 3. Under thermal conditions, pi 3 would be the highest occupied molecular orbital. But this is photochemical conditions. I promote an electron from pi 3 to pi 4. So pi 4 is the highest occupied molecular orbital under these photochemical reaction conditions. So I need to draw pi 4. Pi 4 would have 3 nodes associated with it. You can calculate that quickly by recognizing that pi 1 would have no new nodes, pi 2, 1, new node, pi 3, 2 new nodes, and pi 4, 3 new nodes. I'm going to put one of them right in the middle. Now I have some choices. I could put the other 2 right there and right there, or right there and right there. It really doesn't matter. You're going to get the same answer no matter what. Just make sure you place those nodes symmetrically about this pi molecular orbital. All right, we've got our nodes in place. Let's start shading. Bonding interaction there, but as I pass through a node, it switches. Pass through a node, it switches. Pass through a node, it switches. That's pi 4. The question is, when I look at pi 4, will this ring opening or ring closing happen in a conrotary or a disrotary fashion? Now remember, conrotary means that they're both falling in the same direction. It can be both that way, or it can be both that way. They have to both fall in the same direction. Disrotary means that they're falling in opposite directions. They can fall towards each other or they can fall away as long as they're falling in opposite directions. So that's how we describe conrotary and disrotary. And to be sure, we're focused on the 2 terminal carbon atoms because those are the ones that are the site of the new bond formation. There's the new bond forming right there. This is what we're looking at. Will this sigma bond form to make the ring? Unfortunately, my p orbital over here is kind of tipped sideways, but hopefully that won't disturb you. And you can see that if I allow this p orbital to fall that way and this p orbital to fall in the same direction, then what I would get focused only on this new bond that's forming, what I would get is this p orbital fell that way, so it would look like that. This one's falling in the same direction. It would look like that. That would give me a bonding interaction. If I allowed them to fall in the opposite counterclockwise direction, both of them, it would still be conrotary. Instead of having the two shaded regions overlapping, I'd have the two unshaded regions overlapping. That also represents a bonding interaction, which means that's the way it should go. So this one is going to be conrotary, a conrotary ring closure. Well, here's an interesting one. Here's our last example. We're going to look at a case of an electrocyclic ring opening reaction. But this time, rather than starting with the ring open species, which is the easier way to look at it, we're going to start with the ring closed species. This adds a slight level of complexity to the problem, but really not that much. What's key is that we appreciate that if this thing ring opens, and I've chosen thermal conditions here, if this ring opens, the aeroformalism would look like this. I'd make a butadiene. The question is, what becomes of those methyl groups? Right now in the ring closed version, the methyl groups are trans with respect to one another, but where should they be here? We don't really know. One way to indicate that we don't know whether they should be up or down on either of these carbons is to sort of draw one of these squiggly lines, which means there is a methyl group there, but I'm not sure if I should draw it here or here, here or here. I don't really know where to put them. We're going to figure out where to put them, but right now we don't know. Well, this is a good test of the things we were talking about, because we said in an electrocyclic ring opening and ring closing reaction, whatever you learn by studying the ring closing event is telling you everything you need to know when you study the ring opening event, which is what we're looking at here. And more importantly, regardless of which direction the reaction is shown in, you always examine the highest occupied molecular orbital of the ring open species. So I'm going to go ahead and draw my butadiene. That is my ring open species. I don't really know where those methyl groups are. We're going to figure it out. But I want to focus on the highest occupied molecular orbital of this species under thermal conditions. That would be pi 2. So there's pi 2. And I think you can see that once again, this needs to close in a conrotary fashion. If I allow it to close in a conrotary fashion, when this one tips in this direction, there's the shading. When this one tips in that direction, there's the shading. Whoops, that was out of view. My apologies. When this one tips in this direction, there's the shading. When this one tips in this direction, there's the shading, and I have a bonding interaction. So this is going to be a conrotary ring closure. The last question is, what about the stereochemistry? I'm supposed to ring open this. I've just figured out it's going to be a conrotary ring closure, but that means it's also going to be a conrotary ring opening. I'm supposed to start with this species, which has these trans methyl groups. Where should these methyl groups be on the ring open species in order that I get this conrotary ring closure moving in this direction to give the trans species? Well, if you look down here and you just think about it, what you want in the end is for your methyl groups, which would be off of these two carbons right here, you want them to be trans. That is, you want one of them up and one of them down. Well, since this p orbital here is falling in this direction, placing your methyl group out there, see, it's an sp2 species, so you can put it there or there. Putting it there would allow it to pop up. And this is falling conrotary, so putting it there would allow it to pop down. Or in other words, if we go back to the beginning here, the species that is consistent with this reaction would look like that. In this case, showing it as a ring opening process, we have figured out that the ring opening species would have these two trans arrangements about the two pi bonds down here. Now it's going to turn out that had you chosen both of them cis, you'd also get the same product. In other words, it's also possible that we could have started with this species in which the hydrogens were out and the methyls were in. And you can see why that would work. If the methyl group here is in and this falls down, the methyl group would move down. And over here, if the methyl group is in and this one falls to the right, the methyl group would move up. You'd once again have a trans arrangement. So in reality, there's two answers to this problem. Either this molecule or this molecule on paper would work. In practice, this is much more likely to be the actual molecule one would use, and the reason is quite simple. If you look at the geometry of this compound, when I put this diene in this S-cis conformation, there's a lot of steric hindrance between these two methyl groups. Putting the molecule in this S-cis conformation is going to be required in order to run this electrocyclic ring closure reaction, if we're talking about the ring closure side of things. And so that's just energetically demanding. A lot easier to have the methyl groups oriented, pointing away from each other. But regardless, that's how one goes about solving problems of this type. So I hope this was helpful to you. We went over quite a few examples of both cycloaddition reactions and paracyclic electrocyclic ring closures. I'll see you soon.